So hopefully we can finish potentiometry and then go to colorimetry next meeting. So I know we work on glass electrodes during last time, but I'm not sure if I went over the crystalline membrane electrode. So I think the last say that I can have on this glass electrode, there are some advantages that it has. Okay, so its potential is essentially not affected by the presence of redox agents. Okay, and it operates over a wide pH range. Okay, and it responds fast and function well in physiological system. I think that's just advantages of these glass electrodes, and mostly we could say they're selective for monocovalent cations only because polyvalent ions cannot penetrate the surface of the membrane. Okay, now for the crystalline, if ever we already discussed it. So the main reason, or the main, we could say, crystalline membrane electrode that is being used is what we call the fluoride electrode. So it's the solid state electrode, usually ionic compound, crushed powder, melted and formed, sometimes doped to increase this what we call conductivity, and operation is very similar to the glass membrane. Okay, so if you're going to look at some of the solid state crystalline electrodes, they are very useful in different ions. Okay, but the one that is commonly used, we could say, is the lanthanum fluoride, for the fluoride electrode, ISE. So usually if you have the lanthanum fluoride, as you're going to look at here, so you have here the lanthanum fluoride that is doped, okay, with uranium fluoride, europium fluoride, europium. So the mechanism of this is similar to the pH electrode, with potential developing at the two interfaces. Okay, so the europium 2 plus is less charged than the lanthanum. So whenever there's an ion vacancy that is present there, it occurs for every uranium 2 plus. So a neighboring fluoride ion can jump into this vacancy, thereby moving the vacancy to another side. So the repetition of this process moves the fluoride through the what we call the lattice. Okay, so if you're going to look at the interface that it has here, so you have here a reference solution that has the fixed activity of the fluoride, and then you have here the analyte solution that has what we call variable activity of the fluoride. And in between them, so in a glass pH electrode, you have the glass membrane. So in between them is a lanthanum fluoride crystals that serve as your crystalline membrane. Okay, so they are available on of this one, and I don't know, maybe in a month. Okay, when the package that I sent there to Cermicor, there are 2 fluoride electrodes that I included there. Okay, I'll ask him to bring it to you so you can see it, and maybe one professor will take care of that in AECD. Okay. Now, the next thing that we're going to do, okay, so before we go with the liquid crystalline membrane, we can liquid membrane electrode. We can also say that crystalline membranes are also available that consist of the silver sulfide. Okay, so meron din siyang tinatawag na silver sulfide, and you can also have copper sulfide, okay, or cadmium sulfide. So usually they are what? Divalent cations. So the electrode from these materials, they have electrical responses similar to the electrodes of the third kind. So I don't know if you still remember the electrode of first, second, and third kind. Okay. So these divalent sulfides by themselves are not conductor and they do not exhibit ion selectivity. Okay. So the next thing that we're going to talk about is the so-called liquid membrane electrode. So if you're going to look at this type of membrane, they're particularly important because they permit the direct potentiometric determination of activities of several polyvalent cation and of certain singly charged anions, as well as what we call the cation. So usually, okay, this so-called liquid membrane, okay, they usually consist of organic liquid that are not soluble in the sample and held by the porous disc between aqueous reference electrode and the aqueous sample of the solution. Okay, so if you're going to look at this type of what we call liquid membrane, they are formed from immiscible liquid that selectively bond some of the what we call ions. Okay, so what happened here is the membrane has the ability to selectively bind ions of what we call interest. And the example that we have here of the liquid membrane electrode is the calcium dialkyl phosphate. So if we're going to look at this calcium, okay, dialkyl phosphate, so what you're going to see here is this one. So that is your calcium, okay? And you have here a diphosphate within it. So at the solution and membrane interfaces, so this is what happened. Some of the calcium is dissociated. Okay, so in the solution, you have that one, and then you have an organic membrane surface, and then you also have an organic membrane. So the side of the membrane with the lower activity of the calcium 2+ becomes negative relative, okay, to the other, what we call surface. So we could say the phenomenon or the principle of this is still similar to the glass electrode and the crystalline membrane electrode, okay, where the potential of the liquid membrane electrode develop across the interface between the solution containing the analyte and a liquid ion exchanger that selectively binds the analyte ion. Okay, so the principles are almost the same. So if you're going to look at this, maybe this is how it looks like. So you still have the reference electrode. Okay, so you have the ion selective membrane, the internal electrolyte. So what happened? So this is your sample that comes here. So there's an activity there of the external ion. And then in the internal electrolyte, you also have there, okay, the standard ion that you use for the difference, okay, between the two. So if you're going to look at this, so there's an indicator potential that is equals to C minus 0.0592 over 2, okay, P of calcium. So it's still the same as what we have discussed so far. Usually, if we have this potentiometric, it's always like that. Okay, so we could say liquid membrane electron, they are usually for what? Divalent cation. Okay. So the structure is almost the same. There's always a boundary, the membrane, where you develop a difference between the activity of the target ions that you have in the sample and the internal solution that you have. Pareho lang. Okay. And if you're going to look, okay, at the phenomena that happen here, so it's just based on the potential that develops across two immiscible liquids with different affinities for the analyte. So the porous membrane here, they used to separate the liquids. Remember, the membrane should be what? Insoluble. So if you're going to look at the reaction here, so this is the calcium dialkyl phosphate. Okay, so you have an activity here, okay, of the calcium that is in the sample solution, and then you have an activity here that is known, okay, with the calcium dialkyl phosphate with the reference electrode. So if you're going to look at the reaction that happened here, so this selectively bond certain ions, which in this case is calcium 2+. Okay, so the calcium dialkyl phosphate, they are insoluble in water, but it still binds with the calcium 2+ strongly. So the active membranes here in the liquid, the active substance in the liquids are of three kinds. So it's either what? Cation exchanger, anion exchangers, or neutral macrocyclic compounds, which selectively complex certain cations. So if you read what you're assigned to write, the principle, I think, is still the same here. So it's just like this is the so-called modifier in a potentiometric method. Okay, so you find way wherein you have a material that binds with your target cation. So in this case, it can be a cation exchanger or an ion exchanger. So here we could say, what do you think is this thing here, the dialkyl phosphate? What is its role if you choose between the three kinds of the liquid membrane? Anyone? So since is it what? A negative charge, so that is just can act as an ion exchanger, or we could say it's going to target calcium 2+, but it is very selective for calcium 2+. And if you're going to look at the potential that is developed here, so you can have it like E1, okay, minus E2. And if the activity 2 is constant, so you end up with this N plus 0.0592 divided by 2 times the power of the calcium. And we could say, if we're going to look at the design of the liquid membrane electrode, so this is typically how it looks like. So what can you say about it if you compare it with a pH electrode? What can you say? So if you're going to look at this, the housing is a little bit what? Stable. Where you place the material. Okay. So there's this reference electrode that you have here. So what it do? It contains a fixed concentration of the calcium. So what do you think is the calcium ion compound? So since it is MCl2, so this is just calcium chloride. Okay. So if you're going to look at this, there's a internal aqueous solution in contact with the reference electrode. So aside from that, the internal aqueous solution is also in contact with the exchanger. Okay, so this aqueous solution that you have here, see that? So it's around here. So aside from being in contact with the silver chloride, it's also in contact with this what we call cation exchanger. That's the one where you have the porous plastic membrane that holds the ion exchanger. Okay, so it contains a fixed concentration of calcium chloride and silver chloride reference electrode. So the porous plastic membrane here. So usually they have this as a PVC membrane as one of the material. It contains the ion exchange liquid that separates the analyte solution from the reference calcium chloride solution. And usually you're going to establish an equilibrium at the interface, which can be represented as the reaction that you have here. Not that one, this one. Okay, so this and then forming 2RO3 and calcium 2 plus. So if you're going to look at this, this is very similar in the glass electrode and what we call the lanthanum fluoride. And this is very valuable. Where do you think you use calcium for? Anyone? Saan ang application ng calcium electrode? Anyone? Who there? Uy. Anong application? Hardness? Are you going to spend money just to determine the hardness of water? Usually it happens when you are what we call getting old. Most old people has this problem. And there's an industry of it that sells a product to prevent this from happening. You're familiar with this?
Osteoporosis.
Osteoporosis. Okay. So what is osteoporosis?
Yung sa commercial po, nagde-degrade yung bones ng
Sa commercial.
tao.
Natutunan nyo na talaga sa commercial.
Deficiency of calcium 2 plus membranes.
Okay, so if you notice when people get old, they usually become what? They have a tender bone. Because what happened is there's a washing out of the calcium ion. That's why you need to supply it, okay, in the form of what? Milk with calcium or orange juice with calcium, because osteoporosis is going to happen. I don't know if you notice it. If old people sleep or fall down, they usually get injured because the calcium structure that they have is not really as strong. Now, the calcium level that they have, so sometimes the classic way to determine them is what? Using maybe a redox reaction. The one that you react the calcium to produce oxalate, and then you react oxalate with what? Permanganate to determine the calcium ion. So usually that's we could say the titrimetric analysis that you have there. But with the advent of this calcium membrane electrodes, it's a valuable tool for physiological studies. Remember, you only develop material, or we could say apparatus or tool, if there is always what? A market for it. Okay? So they use the calcium membrane for physiological studies because calcium plays an important role in what? Bone formation. That's the most important thing, but it can also play an important role in nerve conduction, muscle contraction, cardiac conduction, and contraction, and renal tubular function. Okay? If you have high calcium 2 plus, it can also lead to what? Alam niyo yung stones? The gallstones. Okay. So what ano tawag dito? Polyatomic anion, does it react to form a goldstone? That is usually also present in greater amount. Anyone? If you go to med school, you'll be familiar with this. I always use this as an example in my Gen Chem. Calcium phosphate. So calcium phosphate is an insoluble material. So if a gallstone happened, that's one of the products that is formed. So calcium and phosphate, calcium ion and phosphate ion, they're always present in large amount in our body, right? So when you grow old, they are readily calcium 2+ because the calcium that is what we call in the bone, they what we call undergo demineralization, which is the osteoporosis. So the availability of the calcium 2+ reacting with the phosphate. Phosphate is always available on that on our body. Do you agree? Why is it available in our body? Because your phosphate is our what? Main buffer. Remember this reaction? So what's differentiate from this one? Isn't it one phosphate? And we call this what? In biochem. To those who are taking biochem, what is ATP? Sasabihin yung adenosine triphosphate. What does ATP do? Isn't
Energy
that
density.
the fuel that we have? Okay. So that's why we could say this material is very important in what we call analyzing some what we call the cation that is found in our body. Okay, so you can design liquid membrane electrodes for either cations and anions. So if it's a cation, you use a cation exchangers in the membrane, like the dialkyl phosphate. So it is a cation membrane. Okay, it has an anion on it that will exchange with the cation. So if you want an anion, you use an anion exchangers in the membrane. So these are the one where they use. Okay. So water hardness is also what we could use, but not as the one in the calcium 2+. Now the problem with this one, since it is what? Divalent cation. So there's a chance that other divalent cations will also interfere with it. So that's we could say the liquid membrane electrode, and then I have here just some we could say short notes of the other we could say potentiometric electrode. Okay, so one that we have here is the so-called ion sensitive field effect transistor. So this field effect transistor, the metal oxide field effect, so that's what we call MOSFET. So this is a tiny solid state semiconductor device that is widely used in computers and other electronic circuits, which serve as a switch to control the current flow in the liquid. So its main drawback is its pronounced sensitivity to ionic surface impurities. Okay, so what happened when there are other, we could say, ionic surface impurities, it can affect the reading. But this type of material. It's been used since 1970. They were able to take advantage in exploiting the sensitivity of the MOSFET to the surface ionic impurities for the selective potentiometric determination of the various ions. And these studies have led to the development of these so-called ion-sensitive field effect transistors. Now, these ISFET, they offer significant advantages over the membrane electrodes, including ruggedness, small size, inertness toward harsh environments, rapid response, and the low electrical impedance. Okay. And I think one example that they have here is they were able to have an ISFET, okay, for what do you think this measure? Anyone? What ion do you think it measure? pH ion. So what's the difference of this compared to our what we call metallic contact that a typical ISFET would do? So instead of a metal, ano yung ano niya dito? Silicon nitride. Okay. So this is the gate of the ISFET. So if you're going to look at this, there's the analyte solution. So it introduced there. Okay. And what happened? There's an encapsulant between there. So maybe that's the one that serves as your membrane. Okay. So the analyte solution that contains the hydrogen ions is in contact with the insulating layer and with the, where's the reference electrode here? Over this one. So what happened? The surface of the gate insulation functions very much like the membrane, the surface of the glass electrode, since we're comparing this to a pH meter. Okay, so the protons from the hydrogen ions in the test solution, they are absorbed on available microscopic sites in the test on the silicon nitride, and any changes that you have there on the H plus concentration of absorbed protons will result in what? Electrochemical potential between the gate and the source, which it turns the conductivity of the channel of the ISFET. So this is, we could say, a good, what we call the material that they developed during the 1970s. It's called MOSFET, and then it is now what we call turn into the ISFETs, ion sensitive field transistor. Okay, so another thing that we have is the so-called molecular selective electrodes. So if you have a molecular selective electrodes, that means they are developed towards what? Molecules instead of the ions. Okay, so from ISE, we now go to MSE. So these are electrodes designed for the detection of molecules instead of the ions. And what we have here are what? The gas sensing electrode or the gas sensing probes. So typically this is based on ISE that is surrounded by the electrolyte solution. Okay. So what it measures is the activity of the ion measured is affected by dissolved gas. So the gas would enter, okay, the interior solution from the sample by passing through a gas permeable membrane. So maybe we have here oxygen, NH3 and NH4 plus CO2, HCO 3 minus and CO3 2 minus. So if we're going to look at the what we call the gas sensing electrode, so this is what you have, the gas sensing probes. So based on this one, you have a membrane here. And there are internal solution that you have there of the glass electrode. So there's a glass membrane, a gas permeable membrane, and a thin film of the internal solution. So how would the reaction would happen? So let's say we have what? CO2. So this is, we could say, the external solution. And then what happened? CO2 that becomes gas. So this is the one in the membrane force. And then you also have CO2 that is already what? Aqueous, that is in the internal solution. So what can happen in the internal solution? What happens when your CO2 react with your water? Anyone? What's the product?
H2CO2, sir.
Huh?
H2CO2.
H2CO3 minus and
H.
H plus. So what do you think will happen? There's a change in your pH. Isn't it the answer why they said that a tap water is always what? Acidic. Because there's always CO2 that dissolve on it, and the CO2 will form what? An H plus, making the water, we could say, acidic. So we could say this is the mechanism that you have inside this gas sensing probe for carbon dioxide. Okay, so if you're going to look at the overall reaction, what's really happening there? So you have a CO2 aqueous reacting with water to produce H plus and HCO3 minus. So that is the one in your internal solution. And this is the one that you have in the external solution. So how would you look at the thermodynamic equilibrium for this one? K is just equals to what? The activity of your H plus times the one in the internal times activity of your HCO3 minus, that's also in the internal, over the activity of your CO2 that is in your external. And if we're going to look at the potential coming from this indicator electrode, so this is just L prime plus 0.0592 log CO2 external. So this is just one of the example of molecular selective electrode. Now the other one, usually they contain what? A biocatalytic membrane. So whenever we said biocatalytic membrane, that is enzyme. And the general approach is to immobilize an enzyme. So you're familiar with what an enzyme is, right? It's a biological catalyst. So what it do is convert a given molecular analyte into a species that can be measured electrochemically. Okay. So what we need here is an enzyme substrate. So we can have what? so far we know H plus, there's a pH electrode on it. And then the carbon dioxide, there is what? A CO2 gas sensing electrode in the previous example. Now, what happened if you have ammonium ion? What do you think is the enzyme for that? If you want to develop like an ammonium ion selective electrode, or we could say a molecular selective electrode. So you put there the enzyme urease. So what does urease do? Urease would convert what? Urea to NH3 and H plus. So if you're going to look at urea, that's ammonium, NH4, 2CO, plus 2H2O, plus H plus, is going to produce ammonium ion and HCO3, which can break down further into what? 2NH3. So there's a 2 ammonia and 2H plus. So what does it detect? If you have ammonium ion electrode, what does it really detect? It detects ammonia. So we could say this type of what we call biocatalytic membrane electrode, this is an ammonium ion gas sensing electrode. So it's almost the same as a glass electrode, although the membrane that you have here is already what? An immobilized urease. Now the question is, how do you immobilize them? Any idea? How do you immobilize this, what we call electrode? Because the problem with this type of what we call electrode is, how do you maintain the stability of your enzyme? Enzyme is not a cheap material. They're usually expensive. But you can get some of the enzyme from the what we call materials that you have. So it's in some of the potentiometric sensors that we develop, I think some of you are going to write there are some enzymes on those raw materials that we use. Okay. So how do you think they fix, or how do you think they immobilize this thing? So they usually put what? Cross-linking, okay? But if you cross-link, are you sure you're not going to react with the ammonia or with the enzyme? So usually sometimes they just put it, they just stick it in this what we call membrane. Sometimes they put protective membrane. Some they use what we call the sol gel method. But the problem with the sol gel method, the material that you have there could affect the activity of this what we call thing, cross-linking, okay, in ways that the reagent that you use will not affect the activity of the enzyme is another, we could say, good way of immobilizing them. Okay, so you can have entrapment using what? The polymer gel. physical absorption by using inorganic support like alumina. Okay. Covalent bonding of the enzyme to a solid surface such as glass beads or polymer or copolymerization of enzyme with a suitable monomer. So it's a big, we could say, research field. How are you going to do that thing? I don't know if some of you were able to get what is ano ba yung dagta? How do you call it in English? You know what dagta mean? Is it the sap? So some of them contain what? Enzymes. So is it a resin? Okay. Isn't it yung dagta madikit siya? You're familiar what I'm saying? Usually a milky white material, and then sometimes it just stick. Sometimes they can contain materials that you can utilize. I remember I challenged one of the students, if you can give me like that, you can entrap it in the CPE that we're doing before, but unfortunately, hindi yata niya na-gets kung ano gagawin. Because you have a lot of what we call raw materials there that you can study and utilize. Okay. Now, the basis of this one, having this gas sensing electrode has led us to develop this what we call biosensors, which we're going to discuss in a separate chapter. But the biosensors that developed is all, we could say, based on potentiometric titration. The only difference is you put some biological component on it and you call it a biosensor. And one of the things that they use is what? Enzyme. So this is what they have: creatine, the amino acid, glutamine, glutaminase, adenosine, deaminase, glutamate, carboxylase, glucosase. So all of these are, we could say, enzyme for analytes of health interest. And this is how they develop the detectors. So most of them use the gas sensor. What's the first biosensor that was developed? What do you call that? If you read the reading materials I asked you to read, the Clark cell by Leland Clark. And where did he use that, if you remember? Okay. Oxygen. And then he used it to determine sugar. So this is the basis of biosensor, and we will have one meeting that we're going to discuss biosensor. Biosensor is a wild field. Okay. In case you still want to, what do you want to research? And I don't know how many people are doing biosensors there, but none in UP Los Baños for sure. But I think some in UP Manila, and there's a lot in La Salle. Okay. So that's the problem that we have there. Most of the UP alumni, they don't go back to UP Los Baños. Okay. I know some people who are in UP Diliman or in De La Salle. Okay. And if you're going to look at some of the examples that they have, so we could say this is what? An ISTAT 1 portable clinical analyzer. So if you're going to break them down, this is how it looks like. So there's a cartridge level, a sample entry well gasket, a fluid channel, okay? The tape gasket, there's the biosensor chips, calibrant pouch, puncturing barb, cartridge base, and what we call the air bladder. So these are already, we could say, a bedside monitor that is available for some in vitro potentiometric determination of various analytes of biomedical and biological system. So usually I think this one, they're what? Disposable. So everyone you analyze, you change it and then put your sample there. So imagine if you have that thing. I remember me and a collaborator of mine who is still in PNR either. We want something that if we want to test somebody for drugs, all you need to do is what? Put a urine and then put on the chip and see if it is positive for certain drugs or not, illicit drugs or not. Okay. But I went here to the US, he went to Japan, he went back there, I changed my field, so that idea never materialized. But that's the idea that you have. Okay. Another way to look at is this a microfabricated potentiometric sensor for the in vivo determination of analytes. So they're already available. Okay. I'm not sure if you know about the story of the Theranos. Have you heard that? Or we could say the story of Elizabeth Holmes. So if you're going to look at this, what we call microfabricated potentiometric sensor, so you have a reference electrode here, and then you have the ion selective electrodes here. And if you're going to look how many ions they test it. 1, 2, 3, 4, 5, 6. Okay. So usually there are what? 9 ISE on one side of the film and corresponding to the reference electrode. So if you heard the story of Theranos, so Theranos is short for therapeutic diagnostic. So the idea there is with a drop of blood, they can determine all the ions or other molecules of biological interest. So you don't need to get blood from the what we call test tube. You put in the test tube and then analyze them one by one. But unfortunately, the technology is still not possible. Usually, that's the field of microfluidics. 5 years, 10 years, I think that it is possible, but during that time, it's not yet possible. And she was able to get money to start up the thing, $1 billion of money. Okay, and she was what we call dubbed as the next was that an Apple? Steve Jobs. Okay, but unfortunately, she was sentenced that that's a fraud. Okay, and they're using other system in doing their what we call microfluidics. So that's we could say the future of the things here. Okay. Now, an important consideration in the design of an instrument for measuring this what we call cell potential is that its resistance be large enough. Okay, to the cell. If it's not, the IR drop in the cell produces significant error. So most cells containing what? Membrane electrode, they have a very high electrical resistance. Around 100 ohms or more. So in order to measure this potential of high resistant circuits, it is necessary that a voltmeter has a resistance that is several orders of magnitude greater than the resistance of the cell being measured. So since mataas yung resistance niya, you have to use a instrument like voltmeter that has a much greater what we call resistance. If the meter resistance is too low, the current is drawn from the cell, which is an effect of lowering the output potential, resulting to the IR drop, thus creating a negative what we call loading error. So yan yung ano ngayon, yung problem. How are you going to design an instrument that can measure potential directly? So for instance here, okay, the true potential of the glass Coulomber electrode system is 0.8 volts, and its internal resistance is 20 mega ohms. So what would be the relative error in the potential if the measuring device has 100 mega ohms? If you're going to look at the what we call chart here, so this is how it looks like. So resistance of this, potential of this, and then your measuring device has a potential of this one. So Ohm's law, which says E equals to IRS plus IR of M. So I, there is what? The current in the circuit consisting of the cell and the measuring device. So the current is given as what? I equals to E over R, right? So the potential there is 0.80. And how do we do this? 20 plus 100. So since this is mega ohms times 10 to the 6 ohms. So this is equals to what? What's the current that you have here? Around 6.67 times 10 to the negative 9. Tama? So this is what? Ampere. So what now is the EM? EM is equals to what? IR? Am I right? So the current now is 6.67 times 10 to the negative 9 ampere. And then the resistance of the measuring device here is what? 100 times 10 to the 6 to get the ohms. So this is equals to 667. So what's the relative error? So the reading is 0.8, right? So if you have the measuring device, so relative error 0.667 minus 0.8 over 0.8. So that's a negative, right? Times 100. So there's a negative 17% error. So how do we solve this? What do we do? We can what we call increase the resistance, maybe what? 1,000 times greater, so that this one can be brought down to lower percentage error. So that's the problem that we have. And usually what they do is they develop numerous high resistance direct reading digital voltmeters with a resistance that's 10 to the 11 ohms. Okay. So some of them are the pH meters that we have, and other what we call p-ion meters or ion meters that we have. So that's the way they overcome this problem. Now, using this pH meter and other stuff, they would provide rapid and convenient method for determining the activity of variety of cations and anions, right? Usually in seconds, if you dip the electrode, you can already determine the activity or the concentration. All you need to do is compare, okay, the potential developed in the cell containing the indicator electrode in the analyte solution with the potential when immersed in one or more standard solution of known analyte concentration. So we could say the direct potentiometric measurement, what really happened, there's the potential of the cell can be expressed in terms of the potentials developed by indicator electrode, reference electrode, and junction potential. So if you're going to look at this E cell is equals to E indicator minus E reference plus potential, junction potential. And if you have Xn plus or any cation N plus, the response that you have would be what? Nerntion. So the indicator there for the potential L minus 0.0592 divided by N to Px. And if you're going to look at the rearrangement that you have here, so substitution and rearrangement would lead to what? So you have a Px, if you follow the one that we have here, equals to negative log Ax, right? Like pH equals to negative log H plus. So if you're going to look at this, the negative of that, so it's E cell minus the junction potential minus the reference electrode plus L So what's the constant terms that can we combine to give a new constant here? So we can have the E cell minus K over 0.0592. So this is still what we call the Nernst equation. Or we have N E cell minus K over 0.0592. We just brought this up. So if you have an anion A, so that's PA equals to E cell minus K over 0.0592 divided by N, or you can put the N on top. And when the two equations are solved for the E cell, what happened? E cell is just equals to K minus 0.0592 N times Px, or E cell equals to K plus 0.0592 N PA for the anions. So the Nernst equation is still, we could say, applicable here. Now, what's the problem with our electrode? From time to time, you need the electrode to be what? Calibrate. So the electrode calibration method, okay, what it is a method of external standards. So the electrode calibration methods offers the advantages of simplicity, speed, and applicability to the continuous monitoring of Px, cation, or PA, which is what we call anion. So why do we need to do this? Why do we always have to do calibration? In a pH electrode, how do we do calibration? Anyone? I need to do it to the 3 pH meter that was given to me. So you usually put the standard there of pH 4, pH 7, and pH 10. So the lab tech told me if it's still working, go ahead. So I put them in a pH 4 and some of the reading is 4.17, 3.87. So I think it's still possible to fix them. Okay. So the direct electrode calibration method offers the advantages as of simplicity, speed, and applicability to the continuous monitoring of the cation and anion. However, the method has two, we could say, important disadvantages. One is that the accuracy of measurement obtained by this procedure is limited by the inherent, we could say, uncertainty caused by the junction potential. And unfortunately, this uncertainty can never be what? Totally eliminated. Now, the second one, okay, second disadvantage of this method or procedure is that it results from an analysis or activities rather than concentration. So for some, it could be an advantage if you're looking for activities, but if you're looking for concentration, that is what we call disadvantage. So there's an inherent error on the order of more than 1 millivolt in the electrode calibration method. It results from the assumption that K remain constant after calibration. Okay, so you can look at the magnitude of the error here as log of 10 E dAx over AX minus 0.44 dAx of X. So if you're going to look at the percent relative error, so for every change in the activity that you have there, times 100%. So that is around 38.9 N. Okay, times 100. So we could say this one, this relative error that we have here is associated with absolute uncertainty in the change of K in K. Now, it's important to note that this uncertainty is characteristic of all measurements involving cell that contains a salt bridge, and it cannot be eliminated even by the most careful measurements of the cell potential or the most sensitive and precise measuring device. So that's the problem. Okay, but you just need to calibrate that thing, because you're going to have this error. But if you always calibrate your measuring device, it can minimize your error. That's why, as much as possible, whenever you use a pH meter, you calibrate it. That's always the rule. Okay. Now we also look at the electrode response related to analytical activity rather than to analyte concentration. So what do you see between the potential here in terms of activity? So this is the response of a liquid membrane electrode to variations in the concentration and activity of calcium ions. So the question is, why this happen? Why are they not equal? One of them is a little bit what? Linear. The activity is linear compared to the concentration. Why do you think there's a difference between them? Anyone wants to guess? So what they're looking here, activity, concentration. So as you increase the activity or concentration, okay, they have this potential. But the one that is linear is what? The activity. Anyone? What does this mean? From here, going here, going here, going here. What is increasing here? It's a Ca2 plus, so it's an ion. And this is just what what we call a concentration, right? So the one that is affected here is really the concentration. So an increase in the ion activity and the consequent decrease here with the increasing electrolyte concentration results to this what we call non-linearity. So this is commonly, we could say, happening in what we call potentiometric titration. But what do you think is the problem? Yep. So this is just what? A calibration curve, right? So the way that they look at this is the one that is affected here is due to the what we call increasing electrolyte concentration. So when the electrolyte concentrations are not too great, it is often helpful to swam both the sample and the calibration that with the excess of the inert electrode. Yes, Carmel.
Sir, tanong ko lang po, ito pong solid line is for the activity, and then
Activity, yeah.
yung dashed line po ay sa concentration.
Yep. So one of them is linear compared to the other. So the one that is affected here is what? The concentration. So usually what happened here, okay, the linearity is just due to the increase of what? The ionic strength.
Sir, in that case po, kasi di ba po sir, sa activity po tayo nag-take account ng ionic strength po.
Yep. But the thing is, ionic strength is not only coming from your sample, I mean, the target analyte. Ionic strength can also come from what? The other electrolyte that you have. So how do they solve the problem to make sure that it will be linear? In the experiment that we do with fluoride, we add the so-called T-sub. T-sub is what? The total ionic strength adjustment buffer. So what it do, it concentrate, okay, the sample and the standard so that they will not have a great difference in the so-called ionic strength. So ionic strength yung ano dito, effect kung bakit ano. So ang naapektuhan usually is yung concentration. Because isn't it when is activity equal to concentration? Is it at low concentration or at high concentration? Okay, so we have it in the dilute concentration. So what happened if you increase now the ionic strength? So the activity will still be what we call okay, but the concentration is not okay. So how are you going to make this linear? So you have to make sure that you're going to add some ions on it in the form of this what we call T sub. So there's a material that they call T sub, and then you just add it in the solution. So this procedure we could say is done when you're using fluoride. Now another way to do is what? If you have a problem with this one, so maybe you can do some sort of standard addition method. Because in the standard addition, you're just adding known concentration. So to see if what we call your potentiometric measurement is what we call accurate. You're familiar with standard addition? You just spike or add known concentration of the analyte to the solution and then look at the what we call concentration that they have. Now, I'm not going to do this thing. I think that I try to have the time. So if we're going to look at the oral definition. Yes, Carmel.
Sir, sorry po, di ako
Kasi
makarecover.
okay lang. Hindi,
Um,
ang ano lang doon, what happened if the ionic strength is increasing, the activity is what we call a little bit more linear compared to the concentration, but in some aspect, you want to measure concentration in terms of activity. So what do you do? So that maging linear din yung reading ng concentration.
Kasi sir, dun lang po talaga kami nalilito dun sa trend. Kasi if activity is effective concentration, which reflects action or result in non-ideal behavior, then we will expect some deviation sa linearity po. In that case, yung graph po or yung plot dapat ng potential versus activity is the one that is not linear.
Kasi ganito yung explanation sa ano notes ko eh. For this approach to be successful, it is essential that the ionic composition of the standards approximate that of the analyte, a condition that is very difficult to achieve experimentally for complex samples. Okay, so here, mas okay nga yung ano, yung activity, but as I've told you, sometimes, okay, you go after the concentration instead of activity. So for instance, in the fluoride concentration, okay, you rather measure the concentration of the fluoride compared to the activity. So what are you going to do para maging linear siya? Because as you could see here, as it increases here, it deviates. Which is higher? Tingnan nga natin, 10 to the negative 4 and 10 to the negative 1. Di ba mas higher to? Okay. So in terms of the potential, mistaken. The reading of the potential as you increase the concentration, usually hindi nga ganun eh, pababa siya eh. Okay, so what they do here is just in terms of the what we call sensitivity. The change in the potential over the change in the concentration. So what happened? If you're going to look at this when the concentration of your analyte are not too great. I mean, when the electrolyte concentration, because this one is the analyte, right? So what the T-sub do as much as possible is to give enough electrolyte for your analyte to be able to show its concentration, okay? Naapektuhan, okay, if the electrolyte concentration is low. Maybe I try to look at this kasi yung sa notes ko between the two, ito yung nakalabas na charge. I try to look at my other notes and then we can go back on this one. Okay, but the thing is I'm trying to put here is what's the role of the T-sub? Because in fluoride determination, T-sub is usually what we call use. And the explanation that they have is you try to augment or increase the ionic strength, because the ionic strength that you have there, the ionic strength in terms of the electrolyte that you have there would affect the reading that it has. Okay, I'll try to go over with my notes here because I'm just following what is being said here in this what we call figures. But all I know is you need T-sub to improve the reading of your fluoride, okay, especially in complicated samples like water. Kasi maraming ibang present doon in addition to your target analyte. Okay? Now, if you're going to look at the operational definition of your pH, the NIST, the National Institute of Standards and Technology, and IUPAC, they say it's based on the direct calibration of the meter with carefully described buffers followed by potentiometric determination of unknown solutions. That's why it's a must whenever you measure the pH that it should be what we call calibrated. Okay, so if you're going to look at this, it could be like pHs equals to potential minus K over 0.0592. So the ES there, that's the cell potential when the electrodes are immersed in the buffer standards. So if the cell potential is, we could say, EU, like PHU, so you can have it like this. So what's the difference? This is the standard and this is what we call the unknown. So if you're going to compare them, the pH of the unknown is just equals to the pH of the standard minus the potential of the unknown minus the potential of the standard over 0.0592. So yan yung definition, operational definition of the pH. And I tried to, hindi yata kaya. So I tried to what we call incorporate here the other stuff that they use, the potentiometric titration. Okay, and as I've told you, well, in the potentiometric titration, they're not dependent on the measurement of the absolute values of the cell potential. So what they do is just what? Look at the reaction between the titrant and the analyte of known concentration. So the classic example that we have here, we could say is what? The pH meter. So usually you have it like this one, right? And you call this the equivalence point. The what we call the most, ano ba tawag dito? Steepest point in the titration. Now, when you do potentiometric titration, hindi lang siya, we could say, limited to acid base. So whenever you do a potentiometric titration, you use what? Two electrodes, an indicator electrode and a reference electrode. Okay, even the pH meter, it has two electrodes there. the indicator electrode, and the silver-silver chloride. Okay. So one half cell is formed with the indicator electrode and the ions of the analyte, which is generally the electrolyte solution. And the other half cell is formed by the reference electrode. So the overall cell potential is still what we have learned. So E cell is equals to potential in the indicator minus the potential and the reference plus, okay, the potential that you have there in the solution. So where the potential drop between the indicator and the reference electrode over the electrolyte solution, that is given by the potential of the solution. So usually this is how potentiometric titrations look like. It can be like this. If it's a pH or acid-base titration, it could be like this. This one, we observe this in gravimetric or precipitation reaction that we have. So whenever you do potentiometric titration, it involves the measurement of the E cell. So I think typically what we have there is what? Colorimetric. So I don't know if I sent in the group chat the potentiometric titration that we have. We have a halides reacting with silver ion. Okay, so you can have an acid base, a redox titration, a complex symmetric titration, and a precipitation titration. And you can use their what? A pH meter or one with the silver, like what we use in precipitation. Okay. Or one with what we call one that measures the voltage. Usually you do it in the redox. So we have experimented this, and this one. This one, we didn't use the probe or the ISE, but there's always a titration of this one. What's the classic example of a complex symmetric titration? Anyone? EDTA with the hard water, EDTA calcium or EDTA with magnesium. And if you're going to go to the classic one, acid-base titration using a pH meter, do you do this there? Or you just use the phenolphthalein? Hello?
Meron pong phenolphthalein, sir, and then meron din pong exercise for potentiometry.
With a pH meter. And
Yes
what
po,
do you,
pen type.
how do you ask them to plot the results? Is it just the raw data? Or do you ask them
Yeah.
to do what we call, aside from this raw data, do you ask them to do the derivative?
Meron po until first derivative po. Bale, merong plot for raw data and then plot din po for first derivative. Tapos i-compare po yung results.
Do you also do second derivative?
Hindi na po. Tama ba? Hindi na. No?
Di na po, pangit po yung data pag mag-send.
No, I think they should be okay. And then here we do additional one. We have the so-called grand plot. So the same set of data that you have, the problem with using derivatives to find the endpoint is that titration data are least accurate right near the endpoint. So buffering is minimal and the electrode response is sluggish. So what they do is they use what? A grand plot. First time for you to hear that? Maybe
Yes.
those who are teaching chemistry, you can include this one. Okay. So a grand plot is just a plot of the volume of the base times 10 raised to the pH. So you multiply the volume of the base times 10 to the pH, negative pH versus the base volume. And then the grand plot use data from before the endpoint to locate the endpoint. And the slope of the linear portion is the Ka, and the x-intercept is the equivalence point. So how does the grand plot looks like? That one. And then in addition to that, maybe I'll ask you to watch, there's also what we call a grand two plot. So I have a video because there's one experiment that we do that there are asked to do everything, what the raw, the first derivative, the second derivative, and then the grand plot, and then the G2 plot. So maybe that's I don't know. Is grand plot the first time you heard? Now to answer Carmel's thing about the ETA, although I think I cannot finish it one. So for the complex symmetric, wala akong ano ng complex symmetric. There. So usually this is what you have in a complex symmetric. So what's the difference here? 10 to the 4, 10 to the 5, 10 to the 10, 10 to the 16. So what does it mean? This one has a strong binding with the ETA. Compared to this one, compared to this one, compared to this one. So the wider or the steeper the slope is, that means the greater the binding of that metal with the ETA, or the more stable the metal ETA complexes is. Ganun ba yung question, Carmel?
Medyo sir, kasi meron pong 4 na ions, copper 2+, Fe3+, manganese, and chromium. Tapos yung plot po nila, yung
Ganito?
sir, ima-match namin.
Tapos ang given is KF.
Ano sir, potential po versus
So
volume
the
po.
potential is this one.
Opo sir, parang ganito pong plot, sir.
Yeah. Wala. Ano na tayo? Hindi ko natapos. Okay lang. So I will finish it next time and then introduce colorimetry and electrogravimetry. Okay. So I'll try to incorporate everything here. No, the thing is, ito yung KF nila. So the higher the KF, the wider is the what we call slope ba tawag dito? I'm not sure about the question. That's why when they asked me to teach 137, a good thing in chromatography and spectroscopy, they gave me the material in UP Los Baños, so I use it and I just add something. But for the mass spec, the electrochemistry, I have to use my own material, and I'm not sure that's what is being discussed. That's why those who take it would be helpful kung ano yung mga na-cover. So if this is one of them, so that would be helpful to them. Because I think even during my undergrad, we didn't discuss this type of things. So I think I'll end the thing here because overtawad na tayo. Okay. So question. I have to end.